All right, we're going to go through the Unit 6 test, um, and one at a time fairly quickly here. And number one, we're looking at what's happening to the motion of the skateboarder and why in terms of energy. And so initially we've got kinetic energy only. That means this skateboarder is traveling. And as we move forward through time, the kinetic energy gets less and less and less until it disappears entirely. So at the end here, the skateboarder has stopped. So basically the motion is, the velocity is decreasing, and the reason we know that is because kinetic energy is decreasing and dissipated energy is increasing. In questions 2 and 3, we want to do bar graphs. These were 3-point things here, a point for each bar graph and one for the system flow. In number 2, we've got a wagon rolling on a level sidewalk, eventually coming to a stop. So at the beginning, no gravitational energy, no elastic energy. It's entirely kinetic. So we'll just put four bars of that in there. At position B, it's come to a stop. No kinetic, no gravitational, no elastic. All that's left is dissipated energy. So all of that kinetic energy was transferred into dissipated energy. If I was going to do a summary equation, look like this. Pretty simple. The left equals the right. Our system. So we've got a wagon, a sidewalk, and number 3, we have a spring-loaded dart gun firing darts straight up, which then sticks to the ceiling. Okay, so initially we've got all elastic, because while it's cocked and ready to shoot, it's not moving. No gravitational energy, we're near the ground. And then the part afterwards is a little more complicated. And we'll use a drawing to kind of explain what's going on there. So our system is dart gun. We have a dart. We have the ceiling. And we have Earth, because gravity is involved here. Okay, so at the end, I do have gravitational energy. I don't have elastic, that's gone. It's stuck in the ceiling, so there's no kinetic. There's some dissipated. Here's why. If I'd shot the dart in the air and it would have just come back to the ground, there would have been some point where it stopped moving in an upward direction and started falling. And this is a hypothetical. So if we started out with all the elastic, that got transferred right away to kinetic, and then it stopped at the top, this would be all gravitational. But there wouldn't be no upward motion here to give it any kind of velocity to stick to the ceiling. So in fact, the ceiling had to be lower so that it was going fast enough to stick. And so we start out with this thing that is not going to do this path up and down anymore. So at this point, we had some gravitational because it's off the ground, but we also had some kinetic just before it hit. But once it hit, it has the same gravitational energy. Okay, gravitational here and up here are the same, but the kinetic energy was changed into dissipated energy. So I don't know how much of each, but I do know I have both of those. I'm just going to make them equal. They could be any combination that adds up to 4 bars, because there are 4 bars on the left. So our simple equation would have been EE equals EG plus ED. And number 4, 5, and 6, we've got this information here that's kind of important to the problem. We have some known values. We've got a given value of 29,400 joules at the beginning, and that's gravitational energy. So I know that. I also know that the car has a mass of 100 kilograms. And that it's a frictionless track. All right, so at point A, I don't have kinetic energy. It's not moving yet. There's no elastic energy to worry about. The energy is 100% gravitational. The other spot that's easy is point C. And at point C, we have no gravitational energy. It's near the ground. There's no elastic. We don't have to worry about dissipation. The only thing left is, because this cart is moving downhill, at point C, it's all velocity, so it's all 100% kinetic. So at point B, and somewhere in the middle, it's somewhat kinetic and somewhat gravitational. We don't have to worry about elastic. Now we can actually get a pretty good estimate of this, because at point B, we're at 10 meters of height. And 10 meters of height is about a third of the 30. Or we could do the MGH, 10 meters times the gravity of 100 kilograms. Times 9.8. I'm just going to say it's about a third, because I don't know what these bars actually work for. You know, what 4 bars is equal to 29,400, but that's kind of iffy anyway. So I'm going to say that gravitational energy is about a third of 4 bars. And so a third of 4 bars is 1 1/3 bars. We're just going to get a ballpark for gravitational energy. The rest is going to be kinetic, and so that's going to be about 2 2/3 bars. And those two together would add up to 4. In part D, the cart has come to rest compressing a spring, so I have elastic. I have some gravitational because it's off the ground, but I don't have kinetic because it's stopped. At part D, I'm 20 meters off the ground. That's about 2/3 of 30, and 30 meters up at point A was 4 bars, so it's going to be 2/3 of that, so that's 2 2/3 bars gravitational energy, and that leaves the remainder for elastic, and so that's about 1/3. For number 5, we want to know how much kinetic energy the car has at point C, and we don't have information to calculate that correctly. But if I to go back and use my equivalency formulas, where at point A, the energy was all gravitational, and at point C, it was all kinetic. I have this simple equation where gravitational energy equals kinetic energy, and because it's equal to that, and that was given, gravitational energy was 29,400 joules. So is the kinetic energy at point C. So you can explain it like that, or you could calculate it using the formula here. Either one was acceptable. For 6, we want a qualitative energy equation for positions A and B, and we want to use the equation to determine how fast the car is moving at point B. So at point A, we had strictly gravitational energy. At point B, we had some kinetic, and we had some gravitational. We have to be careful, because these two gravitational energies are not the same, so maybe it would be smart to put EGA and EGB here, so we knew that that was at B too. And we want to figure out how fast the car is moving, and so basically we need this value right here. We know the EG at A, we know that was 29,400 joules. It's equal to EK plus MGH. So this up here so you remember what this was. MGH. So the mass was 100 kilograms for the car. Gravity is 9.8 newtons per kilogram. And the height at C, or at B, was 10 meters. And so what we end up with is that EK equals 29,400 joules minus 9,800 joules. And that's the 100 100 times 9.8 times 10. And that's going to give us a kinetic energy of 19,600. Now, this is also equal to 1/2 mv squared. So if I do the work on this, v squared equals 19,600 joules divided by 1/2 times 1/2 divided by I'm thinking here 100. Kilograms. And from that, that works out to 19,600 over 50, about 396, 392. Maybe I should calculate that quick. 392. And so solving for v, I take the square root of both sides, and that's going to be 19.8 meters per second. And number 7, we've got a 7,500 kilogram 18-wheeler traveling 20 meters per second, leaving the ramp, leaving on a runaway truck ramp. Basically, this is a sand pit to stop the truck if its brakes fail. When it comes to a stop, it's 10 meters higher than before. Complete the energy bar graph below. So at the beginning, we have kinetic energy. We have it sitting on a roadway, basically at surface, no gravitational, no elastic. At the end, there's no elastic. We have some gravitational. We have no kinetic because the truck is stopped. And we may have some dissipated. We're going to have to calculate that out. So in the beginning, to find EK, that's equal to 1/2 mv squared, and that's going to be equal to 1/2 times 7,500. Okay, times 7,500 times velocity squared, and so that's 20 meters per second, that quantity squared. And if we do that calculation out, that comes out to be 1,500,000 joules. And we want to figure out if there is any dissipated energy. Our simple formula that we're using, EK, is equal to EG plus ED. And so if I rework that, ED is going to equal EK minus EG. So that's going to equal 1,500,000 joules minus the quantity, this is mgh. So the mass is 7,500 kilograms. Times gravity, which is 9.8 newtons per kilogram, times 10 meters, and that's going to work out to be 765,000. In our last problem, we've got an 8-kilogram box compressing a spring before being launched at a speed of 10 meters per second across a frictionless surface. So in the beginning, we've got a compressed spring, so entirely kinetic. The box is not coming off the ground. Entirely elastic. There's no kinetic energy. It's not moving yet. No gravitational energy. At the end, frictionless, so no dissipated. The spring's released, so no more elastic. No gravitational. It's going to be converted entirely into kinetic energy. Our system is going to be basically the spring plus the block. The energy stored in the spring, we can't get EE directly, but we know that EE is equal to EK, and we can figure that from its final condition, which is moving. And so we just take 1/2 times the mass of the block, which is 8 kilograms, times velocity squared. So it's going to be going 10 meters per second squared, quantity squared. And we're going to be left with then 400 joules of kinetic energy, and because the elastic's equal to that, 400 joules of that as well. And for the final portion of this, what we're trying to figure out, we knew from the prior problem that we had 400 joules of energy. We're looking for the spring constant, which is the letter K. And the formula here is 1/2 K delta X squared. And so I'll just plug in the values for that. You have 400 joules is equal to 1/2 K times delta X squared. So that's 4 meters squared. And so to get that equal, 400 joules over 1/2 and 4 meters squared. And so that's going to equal K. And then, so that's going to work out to be 50. Half times 4 times, or 4 squared is 1/2 of 16, which is 8. 400 over 8 is 50 joules per meter squared, or that would be newtons per meter as a force thing. So this also could be newtons per meter. And that's the solutions for those.